So hello everyone, this is lecture 20 for the classical physics. The last lecture we have discussed about the configurational space. We have discussed everything about the degree of freedoms and how we can find the generalized coordinates and what are generalized coordinates. Okay. So in the last we have found this configurational space, and in this a system is moving from one point to another. So there are infinite ways to follow this. So this was the question, that how can we find that which path will be which path system will take to move from S1 state to S2 states. So this question was answered by the Hamilton. Okay, so it was given by the Hamilton's least action principle. So we'll see what is Hamilton's least action principle. So let's first see the statement. The conservative holonomic mechanical system is represented by a function of generalized coordinates, generalized velocity, and time, which is called the Lagrangian of the system. So this state changing, and every state is represented by holonomic mechanical system is represented by these, means generalized coordinates, generalized velocity, and time. This will be the function of this, and this is called the Lagrangian of the system. So any system will possess these coordinates, means holonomic mechanical system will possess these coordinates, and now they will change in the configuration space from one point to another. Okay, and this is Lagrangian represented by the T minus V. This is nothing but simply kinetic energy minus potential energy. So this is conservative holonomic and mechanical system. For that, Lagrangian is represented by this, and coordinates of Lagrangian will be in the terms of generalized coordinates, generalized velocity, and time. So remember this statement. Now Hamilton said that the system moves from S1 to S2 in such a manner that line integral of the Lagrangian with respect to time takes the minimum possible path. So the line integral of this in this configuration space will give you the minimum path, means the value of which for that Lagrangian for which this will be minimum, this integration will be minimum, that will be your path taken by the system, and we call this action of the system. Okay, so now how you can find that for which Lagrangian it will be minimum, because there are infinite paths, so infinite Lagrangian will be there. So for which it will be minimum. So here comes the Lagrangian to rescue us. So he said that later on Lagrangian proved that the path for which this action have least value can be obtained from the following equation. So this is just a solution of this second order differential equation, means you can find this function as from this. Okay, so Lagrangian said that by solving this for that Lagrangian which validate or verify this equation, we will have the least action, means this value of this action will be minimum for this, means the L which satisfies this equation will give us the minimum action. So now you have the equation. What is this equation? D by dt, complete derivative of partial derivative of L with respect to generalized velocity minus derivative of L with respect to generalized coordinate equal to 0. So if there are n degree of freedoms, then there will be n second order differential equations. Okay, and n Lagrangians we will get. So they all will satisfy the path. So that's how we will get the path, okay, for which it will be minimum. So we will solve the differential equation for any kind of system, and we will find the value of L. So that will be your path which will be taken by the system for which this action will be minimum. So this is just the same as in the Newtonian mechanics, you have ma equal to f. So the same role is playing by this Lagrangian equation in the Lagrangian mechanics. Okay, so and the equation you will get after solving this is called the Lagrangian equation of motion. So we will see some example first, and we will see the previous year questions, what kind of questions are asked from here. Then we will come to this point again, the theory part. So let's see first some examples and questions. By the end of these lectures, you will be able to solve any kind of Lagrangian equations and questions. Okay, so just pay attention here. A particle of mass m is moving in 1D, okay, x direction, is subjected to a Lagrangian this. So Lagrangian of this system is given for a single particle which is moving in 1D, where lambda is real constant. If it starts at origin, so at x equal to 0, t equal to 0, its motion corresponds to equation. So we need to find the equation of motion. Okay, so these four options are given: x equal to a exponential lambda t, x equal to a 1 minus exponential lambda t, x equal to a sine lambda t, x equal to a sine hyperbolic lambda t. So we need to find the equation of motion for this system. Okay, So Lagrangian is given. So first we need to find the least action. So for that we have to satisfy the Lagrangian equation. So these were the d by dt of del L by del Q, means generalized velocity and generalized coordinate. So there is only one independent variable, so you just need the x here. So you will find the L, del L by del x dot and del L by x, and substitute del L by x here, del L by x dot here, and then take the complete derivative with respect to time. Remember this, here it is complete derivative with respect to time, whatever you are getting from here. So you must know how to find the partial derivative and how to find the complete derivative. So they are the must need to solve these questions. So L is given. So after solving with respect to x dot, it will give you this, means m x dot minus lambda x you will get after solving del L by del x dot, and del L by del x will give you lambda m x dot minus lambda x. Now simply taking taking the time derivative, it will give you m x double dot minus m lambda x dot, and after solving this multiply. Simple algebra and mathematics is here, so you will get this equation after solving this. Now this is a second order differential equation, and if you see in my lectures on the differential equation in the mathematical physics, you will be able to solve these differential equations. The solution of this equation will be x equal to c1 exponential lambda t plus c2 exponential minus lambda 2, where c1 and c2 are constants. Okay, so if here it will be plus, then you will get cos and sine terms, means the solution, but here it is minus, so you will get this kind of solution. Must see my all the lectures of differential equations in the mathematical physics. You can find the playlist. So then they will be just a very easy thing for you to solve these kind of equations. Now you have the solution. So for it is given that at origin time was 0. So at time equal to 0 x was 0. So you can find the x equal to 0 when t equal to 0. So c1 plus c2 will be 0. So c1 will be minus c2. Just substitute here. In place of c2 you will write minus c1. So you will get this means c1 exponential lambda t minus c1 exponential minus lambda t. You can divide by 2, multiply by 2, then you will get something like this. Now see, if you have seen my lectures obviously, then this is our sine hyperbolic, means exponential theta minus exponential minus theta divided by 2 is sine hyperbolic theta. So that's how you can write the sine hyperbolic lambda t. So this will be this 2c1, this whole term is this value. So this 2c1 is any constant a, so we'll get x equal to a sine hyperbolic lambda t. So this will be your correct option, D. So I must recommend you to see the differential equations first, then see these lectures. The Lagrangian, let's see one more question. The Lagrangian of a particle of mass m moving in 1D is given by L equal to half mx dot square minus bx. Where b is constant, find the coordinates of the particle xt at time t. So we need to find xt, means value of x changing with time. So this is just an equation of motion we need to find. So we'll use the Lagrangian equations again. So this is a single variable thing. So we will find the del x by del L by del x dot, then del L by del x, and substitute in the equation, the same equation. Then you will get this value as this, and del L by del x will be minus b. Now mx double dot minus minus plus, it will be this x double dot equal to minus b by m. From here you can see that it is del square and d square x by dt square. So 1 dt will go, so you will get dx by dt as minus b by m t plus c1 some constant. Again taking the integration, x will be minus b by 2m t square by 2 plus c1 t plus some constant again. So this will be your equation of motion for this. Means at any time t you can find xt. Now remember this equation, okay? This is very important result. Let's see one more question. These all are the previous year questions, okay? So must pay attention. So first see this figure. There are two walls and a spinning system is tied, and there is this mass m, and this length is L, this length is L, spring constant is k for this, and this is our x direction. Now question is, a particle of mass m attached to two identical springs, each of length L and spring constant k. The equilibrium configuration is 1 when springs are unstretched as shown in figure. There are no other external forces on the system. If the particle is given a small displacement along the x-axis, then Lagrangian of the system is given by. So particle is here, equilibrium condition is when it is unstretched, means in this condition. Now it is stretched along this direction and released. Then you need to find the Lagrangian for the system or the motion of this particle. So we just stretch this something like this, and now you need to find the equation of motion for this, or the Lagrangian for this system. So how you can find? So you need the kinetic energy and the potential energy for this particle. So see, it is bounded to move in this direction only. So its kinetic energy will be half m x dot square. Now what is the potential energy? So potential energy is due to the stretching of this spring from there and from here. So whatever stretch in the spring, it will give you the potential energy, that is kx square by 2. So what is the stretch? See, this is L length, and if this is x, then this length will be under root L square plus x square. So this length minus this length will give you this amount of stretch. So this is kx square. This is the displacement from this, means the stretching in this spring, divided by 2, and there are two springs, so it will be 2 into this potential energy. So it will give you a total potential energy of this particle, and the kinetic energy is this. So T minus V will give you Lagrangian. So just this minus this will give you your answer. So this was in the option, the direct Lagrangian. Now let's see one more question. A particle of mass m slides under the gravity without friction along the parabolic path y equal to ax square as shown in the figure. So in this figure, a particle is in just slipping in this parabolic path without friction under gravity, and this is our reference axis. So particle is moving in this. It is y equal to ax square. Now we need to find the Lagrangian for the system and equation of motion of the particle. So first let's find the number of coordinates, or the degree of freedoms it will have. So it will have 3 coordinates x, y, z, but we know this z can't be equal to 0. So this is one constant, and second is y equal to x square. So we have two constants, so degree of freedom will be 3 into 1 minus 2 will be 1. So only one degree of freedom, means one variable is required. So Lagrangian is nothing but half m velocity square kinetic energy. So velocity at any point will be given by vx square plus vy square. So it will be x dot square plus y dot square, and potential energy will be due to gravity. So this is with this reference axis, so it will be mgh. So h is y here, so minus mgy. Now you need only one degree of freedom, so you can write y in terms of x and can solve the Lagrangian. Okay, so you know y equal to x square, so y dot will be 2a x dot. So just substitute in place of y dot that, and in place of y ax square. So you will get this equation, Lagrangian. Now you can solve the simple equation, that is del L by del x dot minus del L by del x and dy dt of this. So you must know how to differentiate. Okay, so that is a basic need. So you will get the Lagrangian equation of motion by solving this, and this will be your answer. Just verify after solving this. Now let's see one more example. This is not example, these are the previous year questions, which will make you understand what kind of questions are asked and how we apply the concepts. A 1D rigid rod is constrained to move inside a sphere such that its two ends are always in contact with the sphere. Number of constants on the Cartesian coordinates of the ends point of the rod is. So this is a sphere and this is a rod which is always bound to move by touching this surface, means these ends should always be on the surface. Okay, and it can move inside the sphere. So we need to find the how much constant is there in this system. So option was 1, 2, 3, 4. So which option is correct? Means number of constants was either it can be 1 or 2 or 3 or 4. So see, if it is always connected these points, then see this length will always remain radius. So this length is, if this is your origin, so it will be x1 square, y1 square, z1 square equal to this length, means r square, and this is also, so two constants comes from here. x1 square, y1, z1 square equal to r square, x2, y2, z2 square equal to r square. Now third is, this length is always remain fixed between AB, so x2 minus x1 square, y2 minus y1 square plus z2 minus z1 square. So that will be equal to L square. So we have three constants, so answer will be 3. Now let's see one more question. Find the equation of motion of a system described by time independent L. So Lagrangian is given and we need to find the equation of motion. So see, this is a simple, means x dot is given and x is means only one variable is there, and time will be always there because it is in the time and the x. So you can find the values by del L by del x dot, then dy dt of del L by del x dot and del L by x, and then substitute in the equation, you will get your answer. So this is a simple equation, just you need to solve the Lagrangian equation. Again, let's take one more example. A particle of mass m is constrained to move on a plane curve xy equal to c, where c is greater than 0 under gravity L is given by. So a particle is bound to move on this plane xy equal to c. So y equal to c by x. So this graph will be like this. Okay. So the particle is bound to move on this, and we need to find the Lagrangian of this particle, and it is moving under gravity. So gravity reference axis is on x. So at any point the potential energy will be mg by, okay, and our velocity at any point will be vx square plus vy square. So kinetic energy will be half m x dot square plus y dot square minus potential energy is mg by. Now you know y equal to c by x, so just substitute in place of y c by x, and y dot will be minus c by x square x dot. Okay, so just substitute these values and you will get only one variable, that is x inside, and then use the these equation, means Lagrangian equation, and you will get the equation of motion for this particle. So that's it. I hope you understand all the questions. They are basically depending on Lagrangian. In the next lecture we will discuss about the generalized momentum and all. So we will consider theory again, then again some questions, and then you will be able to solve any type of questions, okay, in the question paper of any exam which contains Lagrangian. Okay, then that's it for today. Thank you everyone.